Okay. All right. Right. So again, no class 1 week from today. So I guess today and Thursday will be the last days that I will lecture, and then we'll have Thanksgiving, and then after that there will be student presentations. So I guess for the last couple days, I'm just going to tell you, like, I'm not going to prove stuff. I'm just going to tell you some cool things that I think are cool. I guess a lot of it is my stuff, so I think it's cool for that reason. But yeah, okay, so let me just remind you that the q analog of the number k, which I'll write as bracket k sub q, is just this polynomial 1 minus q to the k over 1 minus q, or in other words, 1 plus q squared plus dot 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 plus q to the k minus 1. And we can also define, I don't know if I did this, but we can define the q analog of k factorial, which is written like this. And this is just where you take the q analog of k times the q analog of k minus 1 times dot 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 times the q analog of 1. Okay, so this is some other polynomial, which is, again, like if you plug in q equals 1 for this, you get k. If you plug in q equals 1 for this, you get k factorial. And then last time I was talking about the cyclic sieving phenomenon. So I said that if x is some finite set, and f is some invertible map from x to itself, and it has order omega, meaning that omega is the least common multiple of the orbit sizes of f. And if capital F of q is some polynomial in the variable q, then we say this triple x f f of q exhibits the cyclic sieving phenomenon if for every integer k, the number of fixed points of f to the k, which is the kth iterative f, this should be this evaluation of the polynomial capital F at e to the 2 pi I k over omega. Okay, so it looks kind of complicated when I say it this way, but the point is that you have this polynomial capital F, which is basically encoding the entire orbit structure of this map F, which is like a dynamical system. And like the nice thing is when this polynomial is something nice that you can write down in sort of a simple way. You can always find some polynomial that will do this by just doing some kind of polynomial interpolation, but that's not so interesting. The interesting thing is when it's like something nice. So last time I was talking about promotion acting on the set of standard Young tableau of a some partition shape, or I guess more generally we could look at the set of linear extensions of a poset. And so I wanted to tell you one theorem which is due to Brendan Rhodes, which I think is pretty cool. So here's the theorem. This is from 2010. Oh, actually, before I state it, let me just point something out. If you have this cyclic sieving phenomenon, then notice that. So, okay, what can I say about capital F of 1? Like, if I take capital F of 1, what is that? Assuming that the cyclic sieving phenomenon holds here, what would be F of 1? You're right, so it's going to be the size of the set x, because I'm just saying, well, you could say I'm setting k equals 0 here, so it's like the number of fixed points of f to the 0, but f to the 0 is the identity map, and everything is fixed by the identity map, so that should be the number of elements of x. So you could think of capital F of q, this polynomial, as like a q analog of the size of x. Okay, so here's the theorem. So suppose lambda is a partition of n. So this, again, this the symbol for saying that lambda is a partition of n. And actually, I'm going to assume it's a rectangular partition. Is a rectangular partition, just meaning that the Young diagram is like a rectangle. Then the triple, where I'll take my set to be the set of standard Young tableau of shape lambda, and I'll take my map F to be promotion, and I'll have some polynomial here. Okay, so the statement will be that this exhibits the cyclic sieving phenomenon. And so my question to you is, what do you think I should put here, based on what I've just said? Hold on 1 second. Okay, so what do you think I might want to put here? So it should be some polynomial such that if I set q equals 1, I should get the number of standard Young tableaux of shape lambda. And we know that there's a hook length formula for the number of standard Young tableaux of shape lambda, which is like in factorial over the product of the hook lengths.
So you write the hook length formula above the analog?
Right, yeah. So basically, well, there are a lot of ways of like getting a q analog of some number, but there's sort of like the most obvious thing you could do here, and it turns out to be the correct thing, which is where you take the q analog of n factorial, and then you divide by the product of the q analogs of the hook lengths. And this ends up being true. Which is kind of amazing, because it's like you're just taking like the hook length formula, which already I think is very cool, and now you're like Qifying it in sort of this obvious way, and now that gives you all of the orbit structure of promotion. And promotion, like a priori, could be this very complicated thing, but it turns out that it's like all the orbit structure is just encoded with this nice polynomial here. Now, I should say that like you could ask if it's necessary that this be a rectangle, and it is. So like, you know, we could have other shapes, and you could try to do the same thing because we still have promotion. We still have the hook length formula for some other shape. You could try to do the same thing, and it doesn't work, which is maybe sort of disappointing. But yeah, it does work for rectangles at least. Okay. So let me give a slightly different way of thinking about promotion. Okay, so here I'm going to let G be a graph. So V will be the vertex set, E will be the edge set. I'll assume it's a simple graph, so there are no loops, there are no multiple edges. It's undirected. Okay, so let this be a graph with n vertices. So I'll define a labeling of G to just be a bijection from the vertex set to the numbers from 1 to n. So a labeling of G is a bijection from V to bracket n. And I'll let lambda sub G be the set of labelings. Of G. So something that I've done before, this is when I was talking about, like, I said that whenever you have a Coxeter element of your Coxeter group, this corresponds to an acyclic orientation of the Coxeter graph. And this correspondence basically went by saying that from the Coxeter element, you sort of you direct each edge basically from the simple reflection that appears first in the Coxeter element to the one that appears later. You can do a very similar thing here. It's basically the same kind of thing, where we say if we're given some labeling, that'll give us an acyclic orientation. So given a labeling sigma in lambda G, we obtain an acyclic orientation of G by directing an edge, well, I'll say each edge say uv, so u and v are two adjacent vertices, and we direct it from u to v if sigma of u is less than sigma of v. So this gives us a poset where the vertices are, well, the elements of the poset are the vertices of the graph, and the order relation is basically saying that to go up in the poset, you just you follow the arrows in this acyclic orientation, essentially. So maybe I should say this. So more formally, this yields a poset. So the elements of the poset are the vertices of G, and I'll call the partial order less than or equal to sub sigma. And this is the poset where U is less than or equal to V if there is a directed path from U to V. So, okay, I've been talking about these Bender-Knuth involutions, but let me define them once again. But now in this setting. So for I in bracket n minus 1, let's define b case of I. This will go from the set of labelings of G to the set of labelings of G by, well, bk sub I of a labeling sigma should be, well, what I'm going to do is I'm going to swap I and I plus 1, which is really just multiplying on the left by this transposition that swaps I and I plus 1. Okay, so it's this. If sigma inverse of I and sigma inverse of I plus 1 are not adjacent. And it'll be sigma if they are adjacent. So it's just kind of like the Bender-Knuth involutions that we had before, where we said, well, in one situation we swap I and I plus 1, in another situation we do nothing. And so the rule is basically you look at you think of the labeling as like you have the labels sitting on the vertices of the graph, and you look at the labels I and I plus 1, and if they're sitting on non-adjacent vertices, you swap them, and if they're sitting on adjacent vertices, you do nothing. So this is actually going to recover the Bender-Knuth involutions that we had before if we look at this poset. So, one more. So if I is between 1 and n minus 1, then sigma and bk sub I of sigma induce the same partial order. This is just because, well, if we're in this case, then sigma and bk sub I of sigma are equal, so obviously they induce the same partial order. But in this case, you've swapped I and I plus 1, but I and I plus 1 are not sitting on adjacent vertices, so you're not actually going to change any of the way that you've directed any of the edges. So they give the same acyclic orientation and therefore the same poset. And also these labelings, so sigma and bk sub I of sigma are both going to be labelings of our graph, and they are both linear extensions of this poset. So also, sigma and bk sub I of sigma are both linear extensions of this poset. And I'll just say and bk sub I is the same as before. And by that I mean, earlier I was defining the Bender-Knuth involutions on a set of linear extensions of a poset, but if you start with sigma, you get some poset, and then you do this bk sub I to it, you get some other labeling, which will be a linear extension of the same poset, and that ends up being exactly the same as if you just had sigma viewed as a linear extension of this poset, and you did the original bk sub I. So let me do an example of this. Here's example. So let's say our graph G looks like this. Okay. And let's say that sigma is this labeling, which I'll represent by just putting the labels on top of the vertices. Yes.
What does BKI is the same as before?
Oh yeah, let me explain that in the example, I guess. I think the example should make that clearer.
Okay.
Like the point is that because, so I can view this as a poset. I can view, because sigma and bk sub I are both linear extensions of this poset, I can think of it as like, I took sigma, which is a linear extension of some poset, and I apply the other bk sub I that I defined like a few classes ago, because now like I defined that on linear extensions of a poset, and I get some linear extension of the same poset, and my claim is that that is the same as this linear extension of the same poset. I think it's confusing the way I've said it, but maybe the example will make it clearer.
So, is the point that if I and I plus 1 are not adjacent, then they're not comparable?
Yeah. Yep.
Because, like, they're adjacent numbers?
Yes.
Okay.
Yep. Yeah, exactly. Okay, so let's say this is V, W, X, Y, Z, V, W, X, Y, Z. And I'll draw the labeling, I guess, in yellow. So here I'll give this the label 1. This will get 3. This will get 5. This will get 2. This will get 4. So I can draw the acyclic orientation by saying, okay, the edge here goes from the 1 to the 3 because 1 is smaller than 3. This edge goes from 1 to 5 because 1 is smaller than 5. This edge goes from 3 to 5. This one goes from 2 to 5. This one goes from 2 to 3. And then this one goes from 3 to 4. And okay, now I can draw, let's do bk sub 1. So here's bk sub 1 of sigma. So I guess I'll start by drawing the same graph as before. Okay, here's V, W, X, Y, Z. I'll do the labels. This is still 3, this is 4, and this is 5. And the point is, when I do bk sub 1, I say, okay, the labels 1 and 2 are on non-adjacent vertices, so I swap them. So now this will be given a 2, this will be given a 1. But now if you draw the acyclic orientation for this thing, you'll see it's exactly the same acyclic orientation as before. And that's because of what Yunso was pointing out, which is that, well, because 1 and 2 are incomparable, well, okay, I'll draw the posets, but like the point is they're incomparable, so you're not changing the acyclic orientation. And now I can draw the poset, and you'll see that V and Y are incomparable in the poset. So here's V, comma, less than or equal to sub sigma. It's this poset that looks like this. this is y, v, w, x, z. I think that should be right. Right, so y is at the bottom, and then v is also at the bottom, and then here's w, and then w is less than z, and w is also less than x. Yeah. And this is also exactly the same as the poset that you would get induced by bk sub 1 of sigma. If I use this, because they're the same acyclic orientation. And so then you can see that, like if I thought of this as a linear extension, this would be giving me, so I guess I'll just draw the labeling here. It would be like, well, okay, the 1 would be on the v, and the 2 is on the y, and those are on incomparable elements. So if I did the original bk sub 1, like the thing defined in terms of linear extensions of posets, it tells me that I should swap the 1 and the 2, just like I did here. Okay. So far I'm just sort of like reinterpreting things in terms of graphs, but there's a reason that I want to do this. So because of this, so this is end of the example. So it makes sense to define promotion as a map from lambda g to lambda g by, well, just the same expression we had before where we said it's this thing. Right, so this is what we used to, or one way we could interpret promotion when we were looking at linear extensions of a poset. And now it also makes sense to do this when we're looking at labelings of a graph. So I had this idea like 2 years ago. So here's the idea. Well, let me do this. I defined, or did I do this? I defined a labeling of G to be a bijection from V to bracket in. I'm going to change this a little. I'm going to change it to Z mod NZ. Okay, that might not seem like I did anything different, because they're sort of the same thing. But I want to think of Z mod NZ as kind of a cyclic object, because I can like wrap around. And maybe more importantly, here I said I'll define bk sub I for I in bracket n minus 1. But let me actually define it for I in Z mod NZ. It's the same definition as before, but now I can do this when I is in. So if I is in, it's the same rule, except the thing is that n plus 1 is 1. So you look at the numbers, basically what bk sub n should do is it should look at the numbers like the labels n and 1, and if they're sitting on non-adjacent vertices, you swap them, and if they're sitting on adjacent vertices, you do nothing. So the idea is define bk sub n, and then we can define a sort of cyclic analog of promotion. So define toric promotion. To be the map. So I'll denote it by T-pro. And it'll again go from labelings of G to labelings of G. And it's just given by, well, I do the same thing as before with these toggles, except I add on bk sub n at the end over here. Okay, so let me give an example of this. So let's say I just take a path graph with 5 vertices. It looks like this. And let's say my labeling is 3, 2, 4, 5, 1. So I want to do toric promotion to this labeling. So the first step is to do bk sub 1. Okay, so I draw this again. And bk sub 1 says look at the numbers 1 and 2, and they're on non-adjacent vertices, so I swap them. So now it's this. And now I do bk sub 2. So bk sub 2 says look at the numbers 2 and 3, they're on non-adjacent vertices, so I swap them. 2, 3. Now I do bk sub 3. So bk sub 3 says, okay, look at the numbers 3 and 4. They're on non-adjacent vertices, so I swap them. Okay, now I do bk sub 4, which says, okay, now I look at the numbers 4 and 5. They're sitting on adjacent vertices, so I do nothing. So I just get the same thing. And then finally I do bk sub 5, which says look at the numbers 5 and 1, and they are on non-adjacent vertices, so I swap them. Okay, so this whole thing is one application of toric promotion. Let me do sort of a continuation of this example. Except I'm not going to draw out all the steps. I'm going to start with this. Yeah. So I start with 3, 2, 4, 5, 1. And what I just computed says that toric promotion sends this to 25314. And now you can just trust me that if you do it again, or if you want, you could work out all the steps, you get 15423. And if you do it here, you get 41352. And then actually, if you do it a fourth time, you get back to where you started. So the thing that I found is that, like, you could study promotion on labelings of a graph. And like there are some cases, like if you're thinking about linear extensions of a poset, and you think of something like standard Young tableau of a rectangle shape that has like nice orbit structure, and I mentioned this result of Rhodes, which tells you, this cyclic sieving phenomenon thing happens. But actually, even in this setting, if you took G to be a path graph and you looked at promotion, so just this, on a path graph, even there, the dynamical behavior is kind of wild. Like it's kind of weird and unpredictable. Well, maybe not completely unpredictable, but like it looks like it's kind of a mess. But it turns out that when you add in the B case of in here, so you make it toric promotion, it actually has very nice behavior. So for example, here's just like an orbit of size 4. And okay, so the theorem that I proved, which I guess was published this year, so if G is a tree, then every orbit of T pro has size n minus 1. So like here, this is a path graph with 5 vertices, so it's a tree with 5 vertices. And this orbit has size 5 minus 1, but actually they all have size 5 minus 1. So I could have put any labeling here, and if I did it 4 times, I'd still get back to where I started. Okay, so that's one thing that I did. So I presented this, there's like a pre-seminar thing that happens at MIT or sometimes here at Harvard. Basically like there's a combinatoric seminar, and like before the seminar, some people meet up and they just like talk about random math stuff. And sometimes it's interesting and sometimes it's not interesting. But I mentioned this at the pre-seminar, and Tom Roby was there, and he had this idea. So basically, Tom Roby's idea was, well, what if you do the same thing to define toric promotion as this composition of these Bender-Knuth involutions, but what if you permute the Bender-Knuth involutions? What if you do like B case of 3, and then you do B case of 1, and then you do B case of 4, and B case of 2, and you just do some weird permuted order? So, idea. So let pi from bracket n to z mod nz be a bijection. So I guess you can think of this as like a permutation, but I'm sort of writing the domain and codomain as like bracket n and z mod nz because I want to think of my set of labels as being z mod nz. And so we can define what I call permutoric promotion. Okay, so it's like toric promotion, but it's permuted. So this is the map. Well, it's going to be a map that I'll call T pro sub pi, and it goes from the set of labelings of G to the set of labelings of G, and it's just given by T pro sub pi is well, bk sub pi of n, and then, well, like this, pi of n minus 1. Okay. So it's exactly the same thing, except I'm using pi to just permute the order of the Bender-Knuth involutions. So I'll tell you a theorem about this in a second. So actually, let me write something here. So I'll define a cyclic descent of pi inverse. This is an element I in Z mod NZ such that pi inverse of I is greater than pi inverse of I plus 1. So it's like a descent, except we're allowed to have n being a cyclic descent. People have studied cyclic descents of permutations, and it's sort of like an interesting thing. I guess maybe more generally I should say that like there's sort of been a lot of attention over the last decade or, I don't know, 10 to 20 years, I guess, of like trying to find cyclic analogs of things in algebraic combinatorics. So like toric promotion would be like a cyclic analog of promotion in some sense. Cyclic descents are like a cyclic analog of descents. And there are various other things that people have done. They're like cyclic Schur polynomials and things like that. Right, and let me put one more piece of notation. So so this is just going to be the Q analog of a binomial coefficient. So A, B sub Q. Well, this is sort of the obvious thing if you want to take like the formula for the binomial coefficient and you just Qify it. So it's the Q analog of A factorial divided by the Q analog of B factorial times the Q analog of A minus B factorial. So this is some polynomial. It is a polynomial. And if you plug in Q equals 1, you get just A choose B. Okay, so here's a theorem that I proved earlier this year with Rachana Madhukara. And also Hugh Thomas. And this was quite a bit harder than I thought it was going to be, but we did it in the end, I guess. Okay, so as before, I'll let pi from bracket n to z mod nz be a bijection. And let's let D be the number of cyclic descents of pi inverse. Actually, maybe I should say how you should think about the cyclic descents. If you take this bijection, you can get an acyclic orientation of the cycle graph from it, where you just say, like think of this as being the cycle graph, and if you have like two vertices that are adjacent in the cycle, then you just look at pi inverse of those two vertices, and you compare which one is bigger, and that gives you the direction that you should draw the arrow. And then the number of cyclic descents is basically like the number of, well, I guess it would be the number of, depending on which way you draw it, let's say counterclockwise arrows, or clockwise if you draw it the other way. But the point is this is like somehow keeping track of the number of counterclockwise arrows if you associate some acyclic orientation of the cycle to this. But anyway, okay, so we have this. So we showed that the order of T pro sub pi, so permutoric promotion, but we're looking at it on the path graph. So turns out that like when you go from toric promotion to permutoric promotion, things get a lot more complicated. And we don't know how to understand arbitrary trees like I did for toric promotion. Here we only look at the path graph, but that, even just the path graph is pretty complicated. So we're going from the path graph, labelings of the path graph to themselves. And well, labelings of the path graph are basically like permutations, right? Because you're just sort of, right? It's like this. You think of this as like the one-line notation of a permutation. So we showed that the order is d times n minus d. And also, we get a cyclic sieving phenomenon. So moreover, so we have this triple, which is the set of labelings of the path graph, and permutoric promotion with this pi. And we have some polynomial, and this exhibits the cyclic sieving phenomenon. I'll tell you what the polynomial is in a second. I'll just say CSP, so cyclic sieving phenomenon. Okay, so the polynomial is n times d minus 1 factorial times n minus d minus 1 factorial times the Q analog. Well, okay. I hope I have enough room. Let me move things over. Sorry. Okay, so it's n d minus 1 factorial, n minus d minus 1 factorial, Q analog of n minus d, except we evaluate the Q analog at q to the d, like that. And then also we have Q analog of the binomial coefficient n minus 1 choose d minus 1, just at q. Yeah. So yeah, it's kind of, well, okay, it's not that bad. Like this out here is like just a scalar. Like the q's are only involved in this. It's like a product of some like the q analog of n minus d, except you replace the q's with q to the d. This is some q analog of a binomial coefficient, so it's not really that bad. And then there's just like this extra numbers out here. Yes.
So what I think is really cool is how it eventually always comes back as opposed to like start somewhere and then go in a cycle.
Well, yes. This is immediate from the fact that it's a bijection, and it's a bijection because it's a composition of little involutions.
Oh, okay.
Yep. But yeah, it's not obvious that it comes back like in this many steps.
Yeah.
Yeah. Any other questions up to here? So Rachana was an undergrad at MIT. Graduated, I guess, last May.
What is she doing now?
So I believe she's in Hungary right now. And yeah,
For
like she's studying like at the, I think the Remy Institute or something. Yeah. Okay, so let me talk about one last topic. This will be the last topic I discuss.
what was Ellie's paper about?
Oh wait, I'll get to that. That's, yeah.
But can you get to today's class? Because I'm not coming on Thursday.
Well, I don't know if I can get through all of it
Okay.
today, but I can start it. And then, I don't know, it'll be recorded. Although I think we're not going to release the recording until Mitchell writes more. Okay, so let P be a poset.
No, like Elliot's still a creature.
Oh, okay, that. Wait, what? Like from 2022?
Yeah.
That I will talk about.
Gonna pick for that.
Yeah, not that one. I'm not going to talk about that one yet. Right. Yeah, so I can talk about that. Maybe I'll get to that today, maybe not, I don't know. Oh, I might, yeah. Okay, so let P be a poset, but I want to assume that the underlying set is like the set of integers from 1 to n. Let this be a poset. Okay, so I don't know if I needed to do this, but recall that I'm going to define, once again, the Bender-Knuth involution, bk sub I, from the set of linear extensions of P to itself. So these things are all kind of related in some way. So this is defined by, well, as before, it's bk sub I of a linear extension U should be U if U inverse of I is less than, in the poset, U inverse of I plus 1. I don't know if this is exactly how I phrased it before, but this is how I want to phrase it this way, or this time. And it's SIU, where here SI is the simple transposition in the symmetric group that swaps I and I plus 1. So it's SIU otherwise. Right, so this is just saying, you think of your linear extension, if the label of, or like if the label I is sitting below the label I plus 1, you do nothing, otherwise you swap them. Okay, so let's define the non-invertible, so it's going to be a non-invertible version of this. Non-invertible Bender-Knuth. I'll call it a toggle instead of an involution because it's not going to be an involution. I don't know if toggle has like a well-defined meaning, but for me a toggle is basically something where you have some definition that like either does nothing or it just like slightly changes your object in some local small way. So this is kind of like what this is doing. But now, okay, what I'm going to do is I'm going to say I define this non-invertible Bender-Knuth toggle, I'll call it tau sub I. This will go from Sn to Sn. And it's defined by tau sub I of U is U if U inverse of I is less than U inverse of I plus 1 in the poset, and it's SIU otherwise. Okay, so it's exactly the same definition that I gave here. The only difference is that I'm now changing the domain and the codomain. So now it's defined from Sn to Sn, but the definition still makes sense. And I phrased it, like I wrote down this definition in a way such that it would extend very naturally to here. So what this is actually doing now is you imagine you have some element of Sn. Actually, let me do an example of it. Okay, so here's my poset. And I want to think of the poset as being a partial order on the numbers from 1 to 4. Here n is 4. So I'm going to put the numbers like inside these little circles. So this is the number 1, and this is the number 2. This is the number 3. This is the number 4. So it's a poset on the numbers 1, 2, 3, and 4. But now I'll also use colors to write a labeling, which is really like a permutation in S4. Okay, so I'll have a 4 here, a 2, a 1, and a 3. So I want to think of this as being the permutation in S4 that sends 1 to 4, it sends 2 to 2, it sends 3 to 1, and it sends 4 to 3. Okay, so 1 goes to 4, 2 goes to 2, 3 goes to 1, 4 goes to 3. And so now I can do these non-invertible Benner-Knut toggles. So let me start by doing tau 1.
Colin,
Yes?
so the white numbers, they have to be a linear extension?
They don't have to be. I've picked it so that they are here, but that's not a requirement in general. I could have had it be like any partial order on the numbers 1, 2, 3, and 4.
So both the white numbers and the yellow numbers can be one other?
Yeah. Yep.
Okay.
So I guess, yeah, one way you can think of this is like, if I think of the set of linear extensions of this, I think I said before that this forms a convex set in the geometric way of thinking about things in terms of the braid arrangement. And like, I could relabel my numbers in the poset, and that would take my convex set and sort of like move it somewhere else. So, yeah. So it can be any partial order on the numbers 1, 2, 3, and 4. And I can pick any labeling. Okay, so if I do tau 1, that says I look at 1 and 2. The 1 is not below the 2, so I swap them. So here I get this. Okay, so that's just sort of like what we had before. So here's tau 2. 1, 2, 3, 4. So if I do tau 2, I say, look at the numbers 2 and 3. 2 is below 3, so I do nothing. Okay, so in this case, it's just 2. Let's do just this again. And then I can do tau 3, and this will be sort of different from before. So tau 3 says, look at 3 and 4. 3 is not below 4. It's actually above it in this case, so I swap them. So here 3 and 4 get swapped like this. So like one way you can think of what this is doing is you're sort of never getting further, you're never getting further away from being a linear extension. So like in this case, the 3 and the 4 were kind of out of order. Like in a linear extension, the 3 is not supposed to be above the 4. So tau 3 kind of put them into the correct order. And tau 1, well, it swapped two things that were incomparable, so it didn't really get you closer to a linear extension, but it didn't really get you further away either. And tau 2 just did nothing, so it also didn't get you like further away from a linear extension. So what we wanted to do, so this started with a paper that I wrote with Noah Kravitz. We wanted to say, like, if you define promotion using these, so like this will be some kind of extended version of promotion, and you do it over and over, probably you should get to a linear extension, because it's sort of like at each step you're either getting closer to a linear extension or you're just not getting further away. So define, I guess I'll call it extended promotion. Or we could just call it promotion, I guess. To be the map okay, I'll call it pro again. And it's just what you get by doing these non-invertible Banner-Knut toggles in this order. And we can also look at like evacuation. So I can define extended evacuation to be the map. I'll call it EV again. This is what you get by doing this partial 1, compose partial 2, compose dot dot dot, compose partial n minus 1, where now partial I is like the extension of what I had before. So earlier I defined it with the Banner-Knut involutions, but now I'm just doing it with the toggles instead. Okay. So like notice that if you have a linear extension, extended promotion just is exactly the same as promotion. Like if you do extended promotion to a linear extension, it's just the same as promotion, because in that case the toggles are just the Banner-Knut involutions. It's the same thing when you're looking at a linear extension. And similarly for evacuation. Okay, so here's a theorem that I proved with Noah Kravitz, who's a grad student at Princeton. Published 2022. Okay, so first of all, I'll say we have, I'll write it as pro to the n minus 1 of Sn equals L of P. So I have my fixed poset P as before. I define the toggles with respect to P, like the definition here is depending on P. And what this is saying is that if you take any permutation and you apply promotion to it n minus 1 times, you get to a linear extension. So it is actually sort of sorting the labelings, which could be out of order, like this one. And it's kind of saying that if you keep doing this extended promotion, eventually you get to a linear extension. And then like the linear extensions, it's a bijection from the set of linear extensions to itself, so it sort of restricts to just a bijection on that set. So like dynamically, it's sort of like everything eventually funnels into the set of linear extensions, and then that has like orbits in there.
So that's for any posets?
Yeah, this is for any poset. Also, okay, so I'm stating this here. We didn't actually write this down in our paper, but it follows from the same argument. So I'll just write it here. If you apply extended evacuation to any permutation, you get a linear extension. So you take any labeling of your poset like this, and you do this composition of these partials like this to do this extended evacuation, then you'll get a linear extension. Also, I should say, like, these are tight in the sense that there are some posets you can construct for which you cannot replace n minus 1 by n minus 2. And similarly, there are some posets that you can construct so that this statement is false. Well, sorry, how should I say it? No. What I said is absolutely wrong. There are some posets that you can construct such that this is false if you replaced EV with like, maybe you cut off like the last thing. So you kind of need like all of these partials to guarantee that you will sort to a linear extension. That's what I meant to say. Okay. So we can kind of think of this as like a sorting procedure on the labelings of a poset. And so I'll define what we call the sorting time of a labeling. And a labeling is, I mean, it's really just like an element of Sn. So define the sorting time of some W in Sn to be the smallest non-negative integer t such that pro to the t of W is a linear extension. So it's the minimum number of times that you need to do promotion to W, like starting with W in order to get to a linear extension. And so what that theorem is saying is that every permutation has sorting time at most n minus 1. And so we were interested in what we call tangled labelings. So say W is tangled. If it has sorting time n minus 1. So like part of the proof of that theorem involved like freezing some elements. So we had like this frozen set of elements, and like, so I wanted to call this tangled because like the Disney movies like Frozen and Tangled. And then like the referee was like what, this seems unnecessary, like why are you calling them this, like you shouldn't. And I was just like, no, we're not going to take that advice. So it's still, we're still doing this. Okay, so also, okay, this is a definition that Elliott gave. So say W is quasi-tangled. If it has sorting time n minus 2. So it's like almost the maximum number. So here's a question. Well, okay, so how many, say, like if you have some poset, you pick some interesting poset, you can ask like how many tangled labelings there are. So like how many labelings are there that require actually the maximum number of iterations of promotion to get sorted to a linear extension. Similarly, you could ask the same thing about the quasi-tangled. So how many tangled or quasi-tangled quasi-tangled labelings does a given poset have? Okay, well, we don't know in general, but we did some things. Okay, so answer, we don't know. In general.
Conjecturally
Wait, what?
Conjecturally n minus 1.
Right, yeah, so we have an upper bound that we've, so I'll mention, yeah, this conjecture. So what we do know, I guess I won't go into the details of this, but Kravitz and I counted the tangled labelings of posets that we call inflated rooted forests. Which are, or maybe I'll just say trees, just I'll assume connected. Inflated rooted trees. Which are sort of like, you can take a rooted tree poset and like blow up each element into like a bigger poset that has a unique minimal element. So like in particular, we understand this when, so actually if you have a poset that has a unique minimal element, it'll have exactly n-1 factorial tangled labelings. So that's one thing we know. But then we have sort of this more general class that we considered. And also Elliott, Hodges, counted quasi-tangled labelings of inflated, okay, so he calls these inflated rooted trees with deflated leaves. So some, I think, slightly less general class, but still fairly general. Oh, and he also did one other thing. Well, I mean, he did a variety of things, but one other thing that I'll mention. So Hodges also found an algorithm to count labelings of P, so some poset P with sorting time n-k-1 for some fixed k, and when P is a rooted tree.
A full and number time algorithm?
I actually don't know. It would probably take a long time.
Okay, so we don't know.
I didn't really think about how long it was. Just
I
like
didn't
you
either.
can do it. Like,
Okay.
But like naively, what if you just iterate all of them?
Right. So presumably it's faster than like
Right, but is it
the
like
most naive thing.
computationally faster? Like,
Yeah,
okay.
I don't know.
Okay.
we just cared about whether or not you could do it. But I guess it gets like slower as k increases.
Yeah.
Because you have to count the ones before it.
Like I think it was, reasonably nicer than just like write out all the labelings and like just check where they go.
No, because you just look at you can like get formulas for, you look at the poset
Right.
itself, and then
Yeah.
you can get formulas from the poset.
Okay, so I guess I have one. So this is going to lead into this paper that we're writing now. Let me see if I have like 5 minutes. Okay, so where I'm heading next time is we're going to take this story that I've been saying here, and we're going to generalize it to other Coxeter groups. And I think this is kind of like a nice example of the theme that I tried to present in this class, where you can have some kind of combinatorial thing, like this is very combinatorial, you've got like labelings of posets. And you can say, well, what if we extend this to Coxeter groups? And so we're going to generalize this in a couple ways. One is that we're going to define these non-invertible Bender-Knuth toggles for any Coxeter group. And the second is that we're going to, compose them in other orders. Like you don't have to do it in this order. You can, and like if you have some other Coxeter group, it's not necessarily, there's like a nice natural order. You just compose them in some order corresponding to the, some Coxeter element of your Coxeter group. Let's see if I'll have time to do this next time. Hopefully I will. Probably will. Yeah, so I think I'll just stop there for now, and then we can talk about the last thing next time.